the last two. Okay, so this is the called the orthogonality of the modal shapes or modal vectors. Modal shapes, most shapes, or we call the modal vectors, or we call the vibration modes. Those kind of the terms sometimes kind of the swappable. And this is a very special properties. And the orthogonal, also that means right, okay, and or 90 degrees, okay. And gonal, that means also is have a feeling of the 90 degrees or right, okay. Basically, this word implying each modal vectors, modal vector 1 and modal vector 2, they are basically if they are orthogonal, basically they're saying in certain way the inner product is 0. Okay, so that is the important concept in vibration unit. So let me give the preparations about before we introducing these words orthogonal. So again, this is our equation of motion, and I've been this one has been expressed in the matrix term. So once we see this one, basically you should assume this as a number degree of freedom can be arbitrary. For example, 2, 3, or n. Okay, and so here is the general form. So for each degree of freedom vectors, that is the components of say n vectors for n degree of freedom. And each has the harmonic form, just like this one we did before. Okay, so basically they are the same template, but with a different amplitude. Okay, and you can see for each term, they simply is in harmonic. So basically, I can take this term out, and so that is the x1 to n. That is the amplitude. With all the notations being introduced, then we can introduce this notation into here. So again, the accelerations for harmonic motion basically is simply is minus omega squared multiplied this amplitude. So again, this is our eigenvalue province. Okay, and rearrange. So I move this term to the right. So basically, this is our another expression of the eigenvalue province. Start from here. Next page, I'm going to talk about this important property. So next page is starting from here. This is where we solved for is the eigenvalue starting point of the eigenvalue province here. Okay, so keep these things in mind. And before this point, we have quite a bit preparation for this. Okay, including formulation of the motions, equation of motion, including the assuming the harmonic motions, okay, and then introducing harmonic motion into this equation of motion. Then we got this one. Okay, this page is a little bit the symbolic calculations, and look at this is a little bit messy, but let me explain this step by step and come to here. So this is the starting point of talking about the orthogonality of the modal vectors. Okay, that is a way here. Okay, so this is a general form. So for different omega, for different natural frequencies, we will have corresponding modal vectors. For example, look at here. If you still remember our notations, this superscript with parentheses that indicating is the modal vectors, say the first mode or second mode, for example. So this one is corresponding to the natural frequencies A, omega A. So that corresponding modal vectors, I use this parentheses A, okay? And in the similar way, follow the same patterns, and with the different natural frequencies B, then I use in B. So here I use the color color code to distinguish. This is corresponding to one mode, this corresponding to the different mode. Okay, so that is starting point. And then move for this one, move from here to here is this. I simply pre-multiply the equations. I simply pre-multiply the whole equations by different modal vectors. Okay, this equation pre-multiply with the different modal vectors. So you can see on the two sides, the left-hand side I pre-multiply, so that is this one here. And on the right-hand side, I pre-multiply to here. Okay, this is the scalar constant. So the scalar constant in the linear algebra can always be on the leading term here. Okay, so basically this equal sign I move to here, and basically from here to here I simply pre-multiply these terms on the two sides. And when we say the pre-multiply, you have to make the dimension consistent. So for example here, if we have a matrix ABCD and say multiply with xy, okay? So if I say I pre-multiply xy with this one, so this is called the pre-multiply that means multiply this one in before these whole things. Doing this, it won't work because in terms of linear algebra, we have to make sure the dimension is consistent. So that means this is 2 by 2, this is 2 by 1. To make that happen, this one you must have the 1 by 2. But apparently this is 2 by 1. So that means if you can transpose this one, then that will make the dimension consistent. So that means this one will be equal to is xy. You have to arrange it in the good way. Okay, so when we do the linear algebra here, when I say the pre-multiply, I put the superscript t. T represent as a transpose of vectors. Okay, good. So that is a notation being used in the textbook. So here again, hopefully you understand the T means transpose, and each of the modal vectors in our textbook, in our lectures, in all my lecture notes, are being expressed in the column vectors. So this one, transpose of a column vector, become a row vector. Nothing special. We simply want to make the multiplication of the matrices consistent in that way. Okay. So basically here, for example, for this example, then basically here we will have a scalar. Scalar is 1 by 1. Scalar, that means a constant. Okay. Okay, in a similar way, in the second equation here, I pre-multiply with the second equation with another vectors. For example, here, this is a vectors. Okay, I pre-multiply these vectors on the both sides. Okay, so that is the equation on the both sides. See? Okay, and then again here for this term, I utilize another properties. Because n is symmetric, so multiplication of the whole terms, I simply can transpose again. So that means after these operations, this term can be to the front, this term can be to the back, but this simply take the transpose like this. Again, this is another properties from the linear algebra I take it. Once I have this one, you can see once I swap, you can see in terms of color code, the two are in the same orders. Okay, so in this way, I simply take the subtractions of this equation from this equation. So I take the minus here. Okay, I take the minus. So the left hand side is this one minus this one. The right hand side is this one minus this one. Okay. So this one, basically this term, again, this term can be swapped. The two color can be swapped. So basically the left-hand side becomes 0. The right-hand side equal to, if you see this one, this is a matrix, this is a matrix, they are the same, but they have a different coefficient. So I kind of distribute the coefficient out there, okay? So that is the result of such, I would say, symbolically a little bit more complicated process. But once we have the numbers, and later I will show you, that will be easier. in terms of the symbols, you can see once we do have the two equations, we subtract from each other the 0 equal to this one. And we know in terms of our exercise from the beginning, the natural frequencies, different natural frequencies are different numbers. So that means the 2 must not be 0. If the whole thing must be equal to 0, the only possibility is this one equal to 0. So we come to the very important equation. This is this one. This one's to this point, and you can try is this. If you don't like this process, that's okay. And just for the first time of the learning, you must listen to my explanation of the whole things. And from this point onward, and as an engineer, then you simply apply the result. So pay attention to my explanation about this equation. This equation is saying this. This is a vector. This is a vector. The vector multiplied with M matrix with another vector, they are 0. So that means the two vectors have an inner product with respect to M, that is 0. So that means the two vectors are orthogonal to each other. So let me put it this way. So for example, this is the modal vectors, and let me put into this x1, x2, xn. Okay, that equation simply is saying is this. x1, x2. This is the modal vectors, and xn, and that is regarding the one modal vectors multiplied with m, m1, m2, mm. Those are 0. M matrix, if you remember, M matrix is diagonal, and all elements of diagonal terms are 0. Times x1, x2, xn. A. This one equal to 0. Okay. And this one is we call the two vectors. Let me use these notations. This one is xb and xa are orthogonal with respect to M matrix. So that is the descriptions of these simple equations here. Example of the orthogonal vectors is like this. And we set and say 1, 2, and say -2, -1 are normal to each other because 1, 2 inner product with -2, -1 equal to 0. Okay. So in the very traditional the algebra, we have this such an idea of the inner product. So that means the A dot B equal to 0, then we know the two vectors are normal to each other, perpendicular to each other in 2 dimensions. Okay, and in general concept, we might set, so here I don't have that one, let me make it up. This one is also equal to 0. That means, because this is redundant, so that basically this expression equivalent to that one. Okay, and for our example here, if we have a modal vectors, say 1, gamma 1, okay, that is our first modal vectors. M1, M2, And second modal vector is 1, R2. Okay, so for example here, this indicating is our first modal vector. And this one is our second modal vectors. If the two, they must be equal to 0. So that one is saying basically is the two particular vectors, they are normal to each other, but not like this. They're normal to each other is through the operation of this particular matrix. So that means here we added up this word called in respect to. Okay? So that is the properties here. And because to this result, we derive is from the very general the process for arbitrary frequencies A and for arbitrary frequencies B, as long as the two frequencies are not the same, these always be satisfied. In a similar process, you can also we can also show the modal vectors also orthogonal, which means perpendicular to each other. The two arbitrary, any two modal vectors are also orthogonal respect to matrix K. Okay, so here is a result. The first relation, this is equation direct result from here. This is a derived equation. Also, we can similarly process. I didn't show it, but we can get this one. So the ij indicating is the i's modal vector and j's modal vectors. As long as they are not the same, this relation always be true. This is called the orthogonal properties, orthogonality of the modal vectors. Okay, that means the two equations. This one, you may say, how can we utilize this? Here will be involving our the next topic, and I will mention that one probably Wednesday. Okay. So this is the properties we obtained from the previous page. Okay, and as long as they are the different modes, and then they always the orthogonal to each others. If they are from the same mode, so for example like this and this, then basically if you operate through M matrix or K matrix, basically you will get is a constant. This one, let me use one example to demonstrate this. So we're starting from the example we have last time. So if you have that note with you, you don't need to rewrite and simply continue from that example here. If you remember, that example is this. So K1 equal to 30 and K2 equal to 5, and this is 10, this is 1. Okay, so this is our x1, this is our x2. So from last time, we obtained two natural frequencies. And then we have the vibration mode. Okay, so that is what we did last time. Okay, and let me demonstrate using the numbers that demonstrate each of the equations here. So first one, we pick I equal to 1, j equal to 2. Okay, so for here, I think I need to give the M matrix. So for our example here, the M matrix equal to 10, 0, 0, 1. And our K matrix equal to 35, minus 5, minus 5, and 5. Okay. So we can exercise here. And did I make any mistake here? Have I made any mistake? Transpose. Good. So that one basically equal to 1, 2. And M matrix is 10, 0, 0, 1. And this is 1 minus 5. Okay? And this one can be easily implemented in MATLAB, but during the calculation, we can do this step by step at the first time. So let me work on the 2 first. Okay? So the 2 basically equal to this row multiplied with this column, and that will be equal to 10. And this row multiplied with this column will be equal to 2, right? Because this is a 1 by 2, this is a 2 by 2. So basically come up with the result is the 1 by 2. So I put into such an arrangement, okay? And then multiply with continuous the remaining 1 minus 5. So this one is 2 by 1. So eventually we're expecting that to be 1 by 1 and scalar. And this one should be equal to 10 minus 10 equal to 0. So that is this one. Good. If your calculation is correct, this must be 0. If not 0, that means something you made a mistake there. Okay. So in a similar way, Q transpose N and x1, and you can exercise, and this one will be also equal to 0. Give a try. Okay. And we can try, say, x1 transpose and multiply with k. We see what happens. So this is 1, 2, and k 35 minus 5 minus 5, 5, and 1 minus 5. Okay, the same thing. And let me work on the first 2 first. So that will becomes 1, 2 multiply with that one, 35 minus 10 equal to 25. And then this one multiply with that one equal to 5. Okay, and then the remaining will be 1 minus 5. So again, this one equal to 0. Okay, so in a similar process, 2 transpose k, and 1, this one is also equal to 0. So that is the numeric demonstrations of the first two equations. As long as you are using the different mode, then the operations with respect to M matrix or K matrix, they must be equal to 0. Okay. Then let me demonstrate the remaining 2 equations. So say right now x1 transpose and n times x1. Okay. So right now I use the first mode. And this one, look this carefully, and this one kind of relating to your number 6 problems in homework 12. So this one, we can do this one. So that is 1, 2, and m equal to 10, 0, 0, 1, 1, 2. Okay, let me see what is the numbers here. So if you do this carefully, and here is my scratch. Okay, so that would be 10, 2, and 1, 2. So okay, 10, 2, 1, 2. So that would be equal to 14. Okay. Should be right? Okay, if now, can you stay for one more minute? Can you hold it? Sure. So here we want to talk about the normalizations of the modal vectors with respect to m. Okay, so basically that one is this. We let x1 equal to any constant, let me call it alpha, and times 1, 2. Okay, so with this alpha, because right now I want to normalize, so basically repeat the same calculation. Right now we have two numbers here, so that is the alpha here. Okay, so we have this one, basically is this x1 m and x1 is transpose equal to 1. You simply finding the tuning scaling factors such that the result equal to 1. So pre-multiply with alpha equal to 14. So from here, alpha you can find is the 114. Then that one you multiply alpha with this one. That is called the normalized vectors. Good. Okay. Go ahead. Sorry. So basically, we say that when we want to normalize the modal vector with respect to m, that means making this number equal to 1. And you try to find what would be the scaling factors for modal vectors to make that happen. Kind of that called the normalization. Normalization is to respect to, always say respect to what kind of the vectors. Good? So basically here I introduce another terminologies. And for any vectors that normalize respect to n, and we call it orthogonal. Orthogonal modal vectors. So that means indicating that vector has to be normalized. Okay, but this term is not that important. Just to let you know that sometimes people kind of using the different words. Okay. Okay. So that is part of these things. So say in the homework problem 6, that one basically you simply doing this. You simply using the different. You're simply using any scaling coefficients, and then your job is to find alpha, making this one equal to 1 rather than 14. You good? Yes.
Is this also applicable for the k value?
Yes. And most of the time in vibrations, the common exercise is we normalize respect to n. That's the common exercise. Of course, you can normalize respect to k. It's no hurt, but the common exercise is respect to n. Okay. The reason why I'm going to explain it. Okay, so then we can exercise for the second mode vectors to see how that goes. Okay. So let me go this one here. So for the second mode, and let me say the beta. Okay, and I do the normalization. Let me do this one separately. So x2 transpose m and x2 will be equal to, that one is 1 minus 5 and 10, 0, 0, 1. 1 minus 5. Okay, the first one, let me work on this one. That is minus 10 and minus 5. 1 1 minus 5. So that would be 35. Okay. So that is our the calculations. So again, to normalize the second modal vector, say let me say that say x2, and let me multiply, do the scaling factor with beta. Okay. So to normalize, that means this one multiply with m with beta x2 equal to 1. Okay, so here we have two betas multiplied together. That's the reason why here we multiply beta squared. Because one beta is a scaling from one vector, another vector have another scaling factor, the beta, so that's a beta squared here. So to do this one, you can see the beta for normalizations, that must be equal to 135 here. You good? So here I do the two different calculations. And then let me try this one. Okay. Try to do this one there. And I'm running out of space. I wish I can draw from. Okay, so right now I'm going to try with K matrix. So x1 and K matrix transpose and x1. So that will be again 1, 2, and K equal to 35 minus 5 is 5, 5, 1, 2. Okay, the result, and I can leave that to you for your detailed calculations, and that equal to 35. Okay, and please leave some space here. I'm going to write that later, but let me do the second mode. One minus 5. 1 minus 5. The result equal to 210. Okay. And this one has not been normalized yet. Okay, but let me show you some magic things. If you compare this number with this number, right now I'm talking about is everything not on the normalized information yet. Okay, if you compare the two numbers, you can see the two numbers have such a special relations. This is equal to 2.5 multiplied with 14. In a similar way, you compare this one with this one. Okay, this one is associated with non-normalized. This one is equal to 6 times 35. Again, right now on this side, the calculation is on the 2. Okay, and the numbers we're showing there is either MII or KII. And here I use the color to specify the very special information. Anyone or can give any more hints or deductions how that's related to omega 1 squared? Yes. So that should be this called the M11. This should be M2. This is always true, as long as your calculation is correct. So, through our numerical calculation, KII is always equal to omega corresponding frequencies times MI. So this is the numbers there. And this one is always true. Doesn't matter if you work on non-normalized or normalized, but let me try, okay? So if we work on the normalized vectors, and let me use the columns to indicate. So here is the calculation corresponding to normalized vectors. Okay, the normalized vectors would be alpha is say alpha square 1, 2, 35 minus 5 minus 5, 5, 1, 2. Okay. So this is the normalized vectors, and alpha equal to where alpha equal to 14. Okay, so that's the number here. So basically, this result, if you do these calculations, then that can basically equal to 2.5 equal to omega 1 squared. Okay, in a similar way, if you work on normalized modal vectors, this one become is beta squared 1 minus 5, 35 minus 5 minus 5, 5, 1 minus 5, and again the result will be equal to omega 2 squared. So, which means if we work on the normalized information, let me summarize here. If xi for I equal to 1 to n are normalized modal vectors with respect to m. Okay, so that is this one. Then these equations basically can be described by transpose m equal to 1. Okay, so what I'm saying is this one, if after our normalization, then that if that is normalized again, so that should be equal to 1, and these equations should be transpose k equal to omega I squared. Okay, so advantage of doing the normalization process is this. So here, that's as I explained, the common exercise is we normalize respect to n metric, because here we put into 1, this is simply is our eigenvalue omega squared simply appear here. Okay? And this is simply a note, and that's the detailed implementations for n-dimensional matrix. That simply is what we did here for 2 by 2. And nothing special. We do details and manually simply expand it like this. Good? Okay, so the one final step, let me summarize everything we have done here. And let me get rid of unnecessary writings, put these things in a better way. So this is 0, this is 0, 0, and this is 0, okay? And let me take the normalized vectors, say for Normalize each modal vectors x1, x2, and xn. Okay. Again, from this moment onward, if I wouldn't emphasize, then you should bear in mind the normalization is respect to n matrix. Okay, and that again, that's a common exercise. So for any normalized vectors, I want to summarize the whole calculations. So that's a normalized I'm going to use is this one. Let me highlight. I'm going to use this one, this one, this one, this one. I'm going to use these notations. I'm going to summarize the 8 pieces of the calculation into very concise expressions in terms of the matrix. Look at this carefully. So I define the modal matrix, and that should be the first time introduced to you, just similar to we call the mass matrix, or stiffness matrix. We have this one. Basically, arrangement is this. For each modal vector, that is a column vectors. Okay, so basically here, this is the first mode, second modal vectors, and the nth modal vectors. We simply put each column vectors into a matrix sequentially. That arrangement. For example, for our example here, and that one simply is this. In our modal vectors is this 1, 14, and 2, 14. So that is the first mode, normalized mode. The second mode is 5, 35, and minus 5, 35. Be good? Okay, you have to follow these notations. We place column-wise into a matrix that is called the modal matrix. Okay, and this is the standard, accepted standard. So you have to pick up the right format in your expressions. So here in our textbook, we're simply using capital X, okay, and indicating the modal vectors. With these things in mind, then for the first element, let me put it into this. Okay, written like this. This one simply is our modal matrix. This one is the transpose of our modal matrix, and hopefully you know what we are doing here. Again, this is a very concise expressions for the result. Okay, so let me get rid of unnecessary information. And this, for our example, this is 2 by 2 matrix. See, this is a 2 by 2 matrix, this is a 2 by 2 matrix, this is a 2 by 2 matrix. So the result must be a 2 by 2 matrix. Okay, and those are the numbers. First number, what is that? Here is the example here. X, Y, let me say A, B, C, D. the first element is obtained by this. Let me implement this carefully. So here for our 0 matrix, that is 0, 0 here. So let me say this is the M1, M2. Okay, how about that? So make up for our M. So basically here we implement the operation of the Q will become X times M1 and Y times MQ. So that is XY. So that becomes X squared M1 plus Y squared MQ. I don't know whether that is successful. Sorry, this is the bad illustrations. Let me right away write this one. This is the result, and this is the X1 transpose M and X1 and X1 transpose M and X2 and X2 transpose M, X1 and X2 transpose M, X2. This is what I need, okay? Sorry, here I skip quite a few detailed steps coming to here. And at this moment, just please take it, okay? And this one, right now with this one in mind, then we can fill in the numbers. So what is this number? This number is given by this one here. This one for normalized is this one, okay? And for this one, if we take normalized, it's this one. The off diagonal, this term is coming from here, 0. This term, 0. In a similar way, the X1 transpose, X2 transpose, and times K matrix times X1, X2. That one can become X1 transpose K, X1, and X1 transpose K, X2, and X2 transpose K, X1, and X2 transpose K, X2. Sorry, a lot of writings. Okay, but speaking of those things, let me fill out the numbers here. This one we're picking up is from here. That is the first modal vectors with K, first modal vectors. First modal vectors K, first modal vectors, that is omega 1 squared. This one is the second modal vectors with K with second modal vectors. That is this one. Second modal vectors with K with second modal vectors, omega 2 squared.
Question.
Let me finish this one. Yes.
So what happens to the beta?
Yeah, beta, that means has been normalized. I'm saying here we talk about it for normalized modal vectors.
Oh, okay.
Right. Okay.
So it's not written in
Yeah.
the matrix, but
Yeah.
the matrix is
Yeah.
normalized.
Yeah. So basically for normalized things, I don't have that conclusions here. So basically for everything, right now for our today, what we have learned for any generic n-equilibrium systems is like this. For normalized vectors, we have this is the modal matrix transpose times n times modal vectors equal to 1, 1, 1, 0, x transpose, okay, transpose equal to omega 1 square, omega 2 square, omega n square, and of diagonal element equal to 0 for normal. Okay, so if you arrange the normalized modal vectors column-wise to form a modal matrix, then this is the very concise but very clean the summaries. We must have this. And all the pieces of information actually has been determined in your eigenvalue province already. So today, what we have spent about 1 hour up to now, this is your take-home message. Basically, what I'm saying is this. From the result of our lectures Friday, you can, based upon that one, right away to write into this. And our previous 55 minutes of the lecture content simply is to explain we have such form. But again, to reach this form, you don't need any additional calculation. Maybe you need one is to normalize the modal vectors. So that reason in problem 6, and I designed a problem for you to manually exercise how to get the normalized modal vectors. And that's the only piece you need to come up with. Okay? So again, this is the take-home message. And then coming back on Wednesday, I will continue to go over the very last topic, and that's called the modal analysis. And that is a super important concept, and also is a very powerful steps. With this one imposed, then basically, in theory, you should be able to solve for all kinds of the linear vibration problems. The modal analysis are based upon the 2 results here. Okay, and that one I will try to give you information for homework 13, and that is the topic under this topic here.